Today, we will focus more on chemical equilibrium, the revision part of it, what all basic terms you need to know. Okay. So first, as soon as an equilibrium is concerned, you should understand a general equation like A plus B giving C plus D is the reaction you are looking into. Got it? Now, reactants will have certain amount of free energy and products will have certain amount of free energy. Got it? Delta G of the reaction implies the free energy of the products, that is summation of the free energy of the products minus summation of the reactants. Got it? Basically, free energy means the available energy of the reactants which can be converted into work. Now, what do you mean by that? That means these reactants can use some part of their energy to convert into a new form, which is products. That is also working. That means this energy which it is utilizing is actually for work. That is to convert into products. Same way, products can also be converting into reactions on the similar lines. If both would happen simultaneously, then we say it is a reversible reaction. Got it? And there are three types of cases you will come across. First case implies that the free energy, if you compare with the reactants to products, maybe it's like this. That is, reactant is here, products free energy is here. Got it? So you can notice that there is a minima that you would get here. Okay, this is with respect to time. Got it? So which means initially free energy of the reactants is very high as compared to that of products. Got it? Which means most of the time reaction will be in the forward direction and very less likely to be on the backward direction. And definitely a situation will arise where the reactants are in very small composition, but the products are in a very high composition. That happens to be at this particular point. So I can say dg by d, you know, this is the eta sign which we use. That is, instead of showing it as timeline, we show it as the reaction progress. This meant the reaction, how reaction is progressing. So you notice that reaction will progress such a way, it will always try to achieve the minimum free energy value. Every reaction will always try to come to the minimum free energy value. Because reactants has a lot of free energy, they want to come to this value. Product has some free energy, they also want to come to this value. So both the directions it will happen at some point of time we will reach this value. So you know that at a minima or a maxima value, differential value will be 0, which means delta G will be 0 at equilibrium. So this is when we reach at equilibrium. And you know that at this point of time, for case 1, if you notice, this is like case 1, I can say the equilibrium constant value has to be very high, at least plus 3 and above. Reason being, reactants have much higher free energy compared to that of products. Similarly, if I plot another case here, which let us call it as case 2, in this case, the reactant's energy is very less, but the product's energy is very high. Reactant versus product. The logic is the same. Delta G with respect to the reaction progress is 0 at minimum point here, and delta G value is 0. And now the equilibrium constant value will be way smaller here. This is the range. Got it? Then we say that the reactants hardly form products, but by chance, if there are any products, they will instantly convert into reactant side. So equilibrium will be more towards the reactant side more than products. Got it? Next, the third case, when both of these equilibriums are substantially maintained at a significant value. That means comparable values like this. This is reactant, this is product, and this is a very comparable value. In that case, it will still achieve an equilibrium. This will be 0. and K equilibrium will lie somewhere between these values, 10 raised to power of minus 3 to 10 raised to power of 3. Correct? See, these kind of reactions where K equilibrium is higher value, way higher value, we see this is almost to completion reaction. These are hardly started reactions. These are at general equilibrium. Got it? So this is the way you need to realize in terms of free energy, everybody. This is the first thing you need to understand from chemical equilibrium. Got it? Now, second thing about kinetics. What is the kinetics part of the equilibrium that you need to understand? So for any chemical reaction, if it is under, if it is a reversible reaction like this, then I can write that rate in the forward direction RF is equal to some rate constant in the forward direction multiplied by concentration of A power A and B power B. This way of writing the equation is called as rate law. Got it? We will be again touching this point multiple number of times. The second time we will touch will be in chemical kinetics. Okay, there I will elaborately explain more in detail about what is the order, what is molecularity, when to write this, when not to write this. Okay, as of now, just remember it like a definition that rate in the forward direction can be written in terms of the reactant concentration raised to the power of their stoichiometric powers. Similarly, rate law also suggests that rate in the backward direction can be written as k backward into a raised to into c raised to power of c and d raised to power of d. And at equilibrium, what is noticed is that the rate of forward direction and backward direction is same. That's why k equilibrium can be written as k forward by k backward, which is concentration of the products upon concentration of the reactants. This is something I'm sure you are aware of it. Just try to recall that part. Okay. This is what happens at equilibrium. Clear? From the kinetics point of view, this much you need to know. Now, notice second thing. Whenever there is an equilibrium achieved, the reactant concentration and the product concentration becomes constant. May or may not be equal, but definitely constant. That means if a reactant is going like this and product is going like this is reactant, this is product, we can say this is the point where equilibrium have been achieved. So this reaction is at equilibrium. Got it? So what are we comparing with? We are comparing with the concentration terms of the reactants and products. Likewise, if I take this and try to plot multiple graphs here, see what are the graphs you need to assess. So second, this same equilibrium can be achieved in this way also. That is where a reactant concentration, product concentration is, constant. That's all you need to take. It might happen that the reactant have a higher value, product has a lower value. Sorry, I wrote it wrong. This is product, this is reactant. Likewise, we can also have a case where a reactant and product have equal values. So this is reactant, this is product. We can say this is where the equilibrium has been achieved. Correct? This is T equilibrium. But if you are writing this in terms of rate, I have only one particular equation to say, that is the rate of reactant should decrease. Correct? This is in terms of rate. So rate of reactant should decrease, that is in the forward direction, and rate in backward direction should increase. And when it reaches equilibrium, when both of them becomes equal, that's when we say equilibrium has been achieved. Okay. So this is the second part you must understand kinetically, how to write the rate and how to express the concentrations, everybody. So I think this part is clear to all of you. Okay. Next, understanding of active mass. What is active mass? Correct? Active mass, for our knowledge, for our syllabus, you need to just understand this as the concentration of the molecules. Concentration of molecules. Okay. Which are actively participating in the reactions. I'm not writing everything, but understand that it is actively participating in the reactions. For example, if you have a solid substance, then how do we measure the active mass? we check out how many moles are on surface. Okay, sorry, moles on surface of the solid substance. How many moles are there on the surface of the solid substance with respect to the surface area? Now what happens is, in the case of solids, this value always remain constant. This value always remain constant, and we assume this to be equal to 1. Similarly, if you have pure liquids, this is when you have pure liquids, there is no other impurity or no other solute been added. Then if you have pure liquid, then also you will simply check out how many moles are present over the volume, correct? And this will also remain constant, and we assume that to be equal to 1. So we say the activity of solids, activity of liquid concentrations, or active masses of solids and liquids, pure liquids, is always 1. Okay. And then if it is a gas, then also we will check out this as moles by volume only. And moles by volume in this case is defined as molarity. Got it? Similarly, if it is solutions, solutions means there is a solute, there is a solvent. In that case also it is moles by volume. And here also we need to check active mass as molarity. So active mass in the case of gases, in the case of solutions, is simply molarity. In the case of liquids and solids, you will take this as constant and the value is 1. Everybody clear? See, generally, you need to understand one factor, that this kind of approach is only valid for dilute solutions. So, if you have dilute solution, dilute solution, in that case, we define that as more molarity term. Okay. But if the solute is in concentrated solution, solute in concentrated solution, then we say its value will always be lesser than molarity. Got it? That's why this equilibrium concept, while writing, we generally write it for the compounds which are relatively at a dilute solutions. Okay, that's why if you compare the solute in water, for example, water always have some small part of H plus ions and OH minus ions. Okay, water's molarity is 55.5. That's very high value. Got it? But if you compare the number of solutes in the concentrated solution here, we can say it is very, very less amount, but the solution is very concentrated. Those kind of cases, we can say we cannot compare that with molarity. I hope this part is clear. Next thing, if in reversible reactions, got it? Ratio of product to reactant, product to reactant is measured, that is called as reaction quotient. Reaction quotient. We write that as Q. And Q is at any point of time before or after equilibrium time. So that is, if T, right, at time T, clear? If Q can be written as product's concentration, right, at time T divided by reactant concentration at time T, that defines the reaction quotient. And it has three things to see. If you are expressing that in terms of concentration, we write it as QC. So QC value will be less than Kc. The net rate is in forward direction. That means the reaction is still going more in the forward direction. If QC is greater than Kc, net reaction or net rate in backward direction. That is in backward direction. And finally, if QC, when it becomes equal to Kc, it is at equilibrium. This is what we need to understand. Clear? As much as the equilibrium constant is concerned and how do we relate with reaction quotient, this is what you need to know. Everybody clear on this point? Right. Now, notice there are two types of equilibriums we need to address. One is homogeneous equilibrium, which means reactants and products, reactants and products are in same phase, Either all of them are in aqueous phase, all of them are in gaseous phase, correct? In that case, we call it as homogeneous equilibrium. Clear? If everything is in a single phase, same phase as in single phase here. So if you have a single phase equilibrium, it is called a homogeneous equilibrium, correct? If you have multi phases, right? We have a gas, aqueous solution reaction, everything is present here. Clear? Now, listen one thing. Suppose if you have a reaction like this, suppose I have uh, A gas plus B gas, and that is giving C gas, clear? And then we have D gas. This is definitely homogeneous reaction or homogeneous equilibrium. Got it? Or if you have all A in aqueous solution, so B in aqueous solution and C in aqueous solution and D in aqueous solution, then this is also a homogeneous equilibrium. This is also a homogeneous equilibrium. Clear? Next, if you have heterogeneous means it has multi-phase. Okay, heterogeneous equilibrium. So simply reactants and products are in multi-phase. Are in multi-phase reactions. Got it? So I'm sure you understand that if you have even one phase is solid, and if it is mixed with, I mean, if at all it is existing in an equilibrium with a gas, then this is an heterogeneous equilibrium. Got it? Even for that matter, let's say there is an ester. Ester is RCOO dash, which is in liquid state, and I'm then adding with water, which is also in liquid state. And after adding that, clear? Now I have got RCOOH. Imagine if it becomes an aqueous state and alcohol R-OH, which is also present in an aqueous state, then this is also an heterogeneous equilibrium. But if all of them remain in a liquid state, then it is homogeneous equilibrium. Clear on that? Right. And any of the phase change reactions are heterogeneous. Phase change reactions. For example, if you have water which is in a solid phase and it's converting into liquid phase. So this is a heterogeneous equilibrium as well. Got it? Second thing, if it comes to features of Kp or Kc, first of all, you know that Kp can be related in terms of Kc as RT delta Ng. I'm sure you know this part. I'm not going to explain much in detail about it. As much as their features are concerned, K equilibrium only depends on temperature. So no matter how much amount of pressure you change, how much amount of volume you change, concentrations we change, they do not affect the value of K equilibrium as long as temperature is constant. Got it? As long as temperature is constant. Clear? Now, next important term you need to understand is degree of dissociation. Degree of dissociation. Especially this is more validated in the case of gases and liquid solutions. For example, if you have a compound, if you have any gas A and it is giving n moles of B, where n is greater than 1, that means it is a dissociation part. So that is 1 mole of a gas is producing more number of moles of gas. So that means it is dissociation. Then degree of dissociation, which is normally written as alpha, alpha is always defined as the amount lost by the reactant upon how much is the initial amount, how much amount lost upon the initial amount. That will be the degree of dissociation in general. Got it? How do we address that? For example, if you have a gas, if you have a gas and it is getting dissociated, suppose if you have a moles initially taken and now it has become some x moles being lost here to form nx moles here. In that case, alpha will become x by a. This is in terms of moles. This is in terms of moles. But same logic I can give it for various cases. What if these two are aqueous solutions? A aqueous solution, B aqueous solution. In case of aqueous solution, we usually use C concentration, C concentration. So instead of moles, we use it as molarity, C molarity here. So out of that C molarity, X molarity is lost and NX molarity has formed. So in that case, alpha will be X by C, which is equal to X is equal to C alpha. This is when you write in terms of aqueous solution. Similarly, if you write in terms of pressure, so imagine if this is a gas and gas, and I'm writing instead of moles, I'm writing them in terms of pressure. So this is like the initial pressure P naught. This has initial pressure P naught. And then from that pressure, some X amount is lost to form NX amount of pressure. Then alpha can be X by P naught. So it all depends upon in which particular case you are expressing, whether you are expressing in terms of moles or concentration or pressure. Accordingly, the alpha value changes. Okay, alpha part changes. Now, we got an idea about alpha. You need to learn how to use it in various cases. The first case that you need to learn is, when total pressure is given. So total pressure, okay, Kp and alpha, relating these two is very, very essential cases. Got it? I'll take one case, just to explain you how it goes. You can apply it for all the cases. Suppose if you have SO3 gas, it is in equilibrium with SO2 gas and half O2 gas. In that case, always you can start with some A moles or you can start with some 1 mole. So you can start with A moles here, and at equilibrium we can say A minus X moles have been lost to form X moles here and X by 2 moles here. And if I define in terms of alpha, alpha is simply X by A. Okay. And how many total number of moles we have here? You can see first, let me write down in terms of alpha. So if I write in terms of alpha, it is going to be A minus, A alpha. This will be A alpha. This will be A alpha by 2. Got it? And now, in that case, if you consider the total number of moles here, the total number of moles in this case will be A plus A alpha by 2. So after this, write the mole fractions here. So mole fractions will be A minus A alpha upon A plus A alpha by 2. A alpha upon A plus A alpha by 2 and A alpha by 2 times of A plus A alpha by 2. So you could clearly notice that the A value is anyway getting cancelled. So that's why it doesn't matter whether you start with initial A moles or whether you start with 1 mole. Okay. Having said that, now if you write in terms of partial pressures will be applying Dalton's law, that is mole fraction into total pressure. So the same things, if I just copy here, multiply that with the total pressure, right? Into P total and P total, that gives you partial pressures. Once you know what is partial pressures, you can find what is Kp value. Kp will be partial pressure of SO2 into partial pressure of O2 power half upon partial pressure of SO3. Substitute these values, you will get this as A alpha by A plus A alpha by 2. Sorry, that A is got cancelled here. So alpha Pt by 1 plus alpha by 2, right? That multiplied by alpha Pt by, you know, we have 2 times of 1 plus alpha by 2 here, whole raised to power of half. that divided by the rest of the value here. So which is 1 minus alpha by 1 plus alpha by 2 into P total. Okay. So this is the way you can relate Kp, alpha and Pt. Depending upon the ratios of the stoichiometric coefficients, you'll get different types of equations. I hope this part is clear to everybody. Okay. Now, another conceptual issue which we always do, which the mistakes which we commit usually, let me show you with an example. Another example. Suppose if the equation itself is given like this, 2 moles of NH3 is giving N2 plus 3 moles of H2. And the Kp value for this is given. Okay. And total pressure at equilibrium is given. At equilibrium, what is the total pressure given? And all of them are gases here. In such case, suppose if the question suggests that initially 5 moles have been taken. Initially 5 moles have been taken. Now you have to express that in terms of alpha. Usually, if you write in terms of alpha, please do not write something like there are 2 moles loss here. So you usually write it as 2x, x and 3x. In terms of moles, it is okay. But if you write in terms of alpha, then how do we write? Go with the definition. Alpha is the amount that is lost by initial amount. So actually the 2x itself is 5 alpha. Okay. So therefore, when you write it that way, now it will become 5 minus 5 alpha, right? And now x will become 5 alpha by 2 and 3x will become 5 alpha, right? Uh, Sorry. If you have 3x here, so the same thing you have to multiply with 3. So how much we will get? 15 alpha by 2. Correct. Now this will be the equilibrium values at that point. So now what I can write? The total number of moles at equilibrium. This is at equilibrium. So that would be equal to 5 minus 5 alpha plus 5 alpha by 2 plus 15 alpha by 2. Correct. So that makes it, this is completely 10 alpha here, right? So 10 minus 5 is 5 alpha. So that makes it 5 plus 5 alpha. So now the mole fractions which you'll write will be 5 minus 5 alpha by 5 plus 5 alpha, and here 5 alpha by 2 into 5 plus 5 alpha, and 15 alpha by 2 into 5 plus 5 alpha. Again, have you noticed that this 5 is initial part of 5 you take or 1 you take? It does not make any difference. It will get cancelled off. Okay. So please be very careful while doing it with the stoichiometric coefficient, which is initially given as 2 here. Clear with this part, everybody? Okay. So this is the first part. Everybody must understand how it goes. Right now. Second thing, let's understand how the temperature dependency of equilibrium is. Okay. So temperature dependency of equilibrium. Got it? Now in thermodynamics, if you don't recall, don't worry about it. But what I'm trying to say, for any species having free energy, free energy utilized, if the free energy of any species is utilized, correct? If you are using, then there is some change in its free energy. We can always address that free energy in terms of VdP minus SdT. Okay. So as of now, don't worry about the derivation of this. Remember it the straight away. This formula to be applied. Any species, any substance, if we know that its free energy it is being used. Now it could be used in a chemical reaction. It could be directly used in the form of some expansion or compression of a gas. It could be used in the form of phase change. In any case, as long as a substance is given, whether it is in a liquid state, solid state, gaseous state, doesn't matter. Its free energy change can be expressed in this particular equation. Got it? Therefore, if at all I have a reaction like A plus B is giving C plus D here. So that means here there is some free energy change of A, free energy change of B, free energy change of C and D. So I can write this as A times of small free energy change of A, here it is B times of small free energy change of B, C times of small free energy change of C, and D times of small free energy change of D. And therefore, D of delta G of the reaction, delta G of the reaction means product's free energy minus reactant's free energy. So therefore, we write this as C of delta G of C plus D into delta G of D. This is all the react products free energies minus A into delta G of A plus B into delta G of B. Right? Now, if you are operating at constant temperature, if you're operating at constant temperature, you know that in that case, this part will become zero, correct? And whatever free energy change which you have, now you can express that in terms of VdP. Now, when you put this into VdP, correct, and then integrate everything, because now I have to do not write to have to write everything here. I'm directly writing the equation. Then integrate everything. Then I'll get delta G of the reaction is equal to something called delta G naught of the reaction plus RT ln Q. And Q here base QP. QP here represents the pressure of the partial pressure of the C raised to power of C, D raised to power of D, partial pressure of A raised to power of A, and B raised to power of B at any time t. Now, at equilibrium, what would happen? At equilibrium, we just learned in the first thing today that delta G of the reaction will always be zero. Hence, delta G naught of the reaction will be equal to minus RT, and you know that QP will become KP whenever it is at equilibrium. Got it? And we also know that delta G naught can be represented, delta G naught of the reaction can be represented in terms of enthalpy change of the reaction minus T into entropy change of the reaction. Okay. And delta H naught and delta S naught values are constant values at in the range of temperature. So that means even if the temperature is changing, the delta H naught and delta S naught values does not change. So if you put that logic here, I will get this as minus RT ln Kp is equal to delta H naught minus T delta S naught. So from here I can get ln Kp is equal to minus delta H naught by RT plus delta S naught by R. So this is a very, very important equation which we will be using a lot of times here. And JEE Advanced usually encourage a lot of problem solving from this particular equation onwards. Okay. So please be very clear in terms of understanding how to use delta ln Kp value in terms of delta H naught. Okay. Graphically, if you notice that you can clearly make out that if you are plotting ln Kp versus 1 by t, ln Kp versus 1 by t, it is like a straight line equation with a slope here, with some intercept here. Now the line could go either direction with a positive slope or a negative slope depending upon delta H naught of the reaction. If delta H naught value is less than 0, you'll have a positive slope. If it is greater than 0, we will have a negative slope. This is for an endothermic change. This is for an exothermic change. And you know that if Kp value is increasing, which means reaction moves in the forward direction, moves more in the forward direction, and vice versa. If it is decreasing, it will go in the backward direction. Hence, as temperature increases for endothermic reaction, clear, you would notice that Kp value actually increasing, while as temperature increases for exothermic reaction, correct, the Kp value is in fact decreasing. So it shows that endothermic reactions are most favorable. Okay, these are favorable at high temperature, these are unfavorable at high temperature. So if it is low temperature, then exothermic are more favorable, endothermic are less favorable. Got it? If I write this equation in terms of two different temperatures, I can get this as ln K2 by K1 is equal to delta H naught of the reaction by R into 1 by T1 minus 1 by T2. And this equation is called as Van't Hoff's equation. Van't Hoff's equation. Clear? Now, is it only for homogeneous or heterogeneous reactions? No. This equation can be applied to any type of equilibriums. It could be a physical equilibrium or a chemical equilibrium. What does that mean? See, in case of a physical equilibrium, in case of a physical equilibrium, what is a physical equilibrium? Suppose if you have H2O liquid, it is in equilibrium with H2O gas here like this. Okay, this is a physical equilibrium. In that case, you know that Kp value will be pressure of H2O divided by H2O is in a pure liquid form. For pure liquid form, the active mass is 1. So it means the Kp value is simply the partial pressure of H2O. That's it. Hence, you apply this value directly here. So I will get ln P is equal to minus delta H naught of what do we call the change when you have phase change from liquid to gas? We call the heat evolved as vaporization. Sorry, heat required is called vaporization. So minus delta H of vaporization by RT plus delta S naught of vaporization by R. Okay, this is the general equation. And if I put this back into this Van't Hoff's equation, now it looks like ln P2 by P1 is equal to delta H naught of vaporization by R into 1 by T1 by T2. So basically you have modified the same equation now for Van't Hoff's equation. Now these pressures, these partial pressures, in case if it is water, we call it as water vapor. So this P2 is the vapor pressure of water and P1 is the vapor pressure of water at temperature T1. Okay. So this, if you are expressing the Van't Hoff's equation in terms of vapor pressures, you call it as Clausius-Clapeyron's equation. Got it? So same equation, but different idea. Uh, used for different cases. Clear? So I hope all of you understood. If anybody has any problem, please do ask. I'll just give you a minute. One more type of questions, one more type of theory-based questions, which are usually asked in JEE. That is about relative humidity. That is about relative humidity. Got it? Now, what all basically relative humidity by definition, you know what it is, right? RH. RH is, vapor pressure of water, which is actual value, correct? Divided by vapor pressure of water, which is when it is saturated value, when it is saturation. This saturated vapor pressure is also called as aqueous tension. So sometimes the formula is given like this: partial pressure, vapor pressure of water divided by aqueous tension into 100. This is if you notice it as a formula. Got it? Now, there are 3 points. I will write it down here as well. So learn it properly. Okay. See, partial pressure, if partial pressure of water, if partial pressure of water at equilibrium is is less than vapor pressure of water. If it is less than vapor pressure of water, clear? Then it will absorb then it will absorb water from atmosphere. It will absorb water from atmosphere and reaction will go in backward direction. backward direction. Backward direction means what I'm talking about. I'm talking about this equilibrium. H2O to H2O gas. In this case, equilibrium will go in the backward direction. Got it? Now, same statement, let me rewrite once again. Got it? For the same equilibrium, everybody, if it is greater than, if it is greater than vapor pressure of water, then in that case, it will release water. It will release water into the atmosphere. Release water to atmosphere in the form of vapors, and reaction will go in the forward direction. In the forward direction. Got it? Clear? For example, if you notice that at 0 degrees Celsius, clear, partial pressure of water, partial pressure of water generally is 1.52 torr units. Okay, got it? Clear? Now, if this is the case, it will go in the backward direction till the atmospheric pressure is also becoming 1.52 torr. Right? Once it becomes atmospheric pressure, sorry, not torr, ATM. No, torr only, sorry. 1.52 torr. So when it becomes 1.52 torr, if atmospheric pressure becomes 1.52 torr, I mean the vapor pressure in the atmosphere, my mistake, vapor pressure in the atmosphere becomes 1.52 torr. Till that time, the reaction will go in the forward direction. Once it becomes 1.52 torr, right, it will be at equilibrium. If the vapor pressure in the atmosphere is greater than 1.52 torr, then it will go in the backward direction. Correct? Now, usually we will say that SrCl2 is, SrCl2 or for that matter, BaCl2 are good drying agents. Drying agents. Okay, clear? What do you mean by that? Good drying agents means if it comes to normal pressure, if you are keeping it a normal pressure, the usually atmosphere, the vapor pressure and the atmospheric pressure will be lesser, sorry, more. So what will these do? They will absorb the moisture from the atmosphere. So that's why they are, sorry, yeah, they'll absorb the moisture from the atmosphere, hence making the moisture more dry. That's why they are called as the drying agents. All right. Next, same logic for Na2SO4, if you compare, correct, it will be to be more efflorescent. Efflorescent. Clear? What does this mean? Efflorescent means it will give away water more easily into the atmosphere. Usually Na2SO4 will be with dot 10 H2O and it will give away Na2SO4 solid plus 10 H2O into vapor phase over the time. What does that mean? The partial pressure of H2O, correct, is less than 7.6 torr, correct? And usually this is the value, at room temperature, correct? And partial pressure of H2O when it is in saturation, it is given as 15.2. It is 15.2. So sorry, in that case I can say partial pressure of H2O if it is less than 7.6 torr, which means relative humidity will be less than 50%. Correct? Then we say because the partial pressure of H2 is less than 7.6 torr, the reaction will go more in the forward direction. I hope this part is clear, everybody. So just keep this in mind. One or two questions are there. When I discuss, I'll show you how to solve the questions also. Okay. The next thing we need to learn is about Le Chatelier's principle. Le Chatelier's principle. Instead of going through the theory, I'll directly go through the application part here. Okay? So, uh, if you have any reactions here, I'll take two types of reactions. One is homogeneous, one is heterogeneous. Suppose I have NH3 gas, it is giving half N2 gas plus 3 by 2 H2 gas. If this is the equilibrium given, Kp is given here like this. Okay. So in that case, what I can say, if you add NH3 or remove N2 or H2, correct? Then reaction will move in the forward direction. Kp remains constant. Kp does not change. Got it? To get this constant only, the reaction is moving in the forward direction. Second, if, I mean, addition and removal is clear. Similarly, if you increase the pressure of the system, pressure of system, pressure of system, because all the equilibriums are achieved only in closed system. So if the pressure of system is increased, correct? That means volume of the system decreases. Volume of the system will decrease. When volume decreases, it will choose a direction where number of moles are decreasing. So number of moles are decreasing are in the backward direction. So reaction will go backward. Kp to remain constant. Got it? This is what would happen. Okay. And if I give you delta H of the reaction here is less than 0, which means it is exothermic. So if temperature is increased, Kp value will actually decrease and reaction will go in the backward direction on higher temperature. Got it? This is the effect of temperature. Second thing, adding inert gas. Adding inert gas. If you are adding inert gas, there are two things you need to address: if the volume change is there or not, or if there is a pressure change there or not. If there is no volume change, then there is no effect on equilibrium. If there is no pressure change, which means the volume has to increase. If volume is increasing, reaction will shift. Reaction will shift towards more moles. More moles. In this case, where are the more moles? In the forward direction. So reaction will move in the forward direction if inert gas is added. I think this part is clear, everybody. Just notice with an example. If there is anything bothering you, you can ask me right now. Clear? Okay. So having said these points, now next thing we need to understand is about simultaneous equilibrium. Simultaneous equilibrium. One of the simultaneous equilibrium we learned that in ionic equilibrium, correct? It is in a similar lines, got it? If you are using any of the reactants or products in multiple equilibrium equations, then that is going to be simultaneous equilibrium cases. Okay. So usually you need to check out, any one of such cases here. I'll take one simple case here. Suppose if at all I have A plus 2B is in equilibrium with 3C, correct? And then I have some D plus 4B is giving out 5E this way. Now, if both of these reactions are happening in the same container, consider all our gases, okay? Consider all our gases. Now let's say if I write in terms of pressure, I can write it as initially this is P naught, clear? Or let's say initially I call this as P1 and P2 gas. There is nothing of this one here, clear? And this is P2 as well, 0. And this is P3 gas. So initially I had A, B and D. The pressure of gas is A is P1, this is P2, this is P3. In that case, how do we write the equilibrium for both of them? You see this way. P1, if there is X amount of pressure lost, then from P2, there must be 2x amount of pressure lost. That should appear as 3x in the case of C. And this is when it is Kp1 and this is when you have Kp2. Similarly, if this is P3 and some Y amount is lost, then out of this P2, already 2x was lost here. On top of that, now you are losing 4y also to produce 5y. Okay. And because you have shown the loss pressure of 2x here, the same thing you have to show it here also. So minus 4y. Okay. So now the total pressure by chance, if it is related in the questions, it is about PA plus PB plus PC plus PD plus PE. So in this case, it will be P1 minus X plus P2 minus 2X minus 4Y plus P3 minus Y, right? Sorry, plus 3X plus 3X plus P3 minus Y plus 5Y. Okay, plus 5Y. So that will become the total pressure. Clear? So this is how you need to relate the simultaneous equilibrium questions. Got it? In ionic equilibrium, how to relate that I have already given you earlier. Okay, don't have to worry about that part. Clear? Right. Next thing, in fact, the last thing that you need to know from this topic, theory wise, that is about physical equilibrium. Physical equilibrium. So when it comes to physical equilibrium, there are two types of solutions that you need, two types of phases that you need to address. One is, you know, water as an exclusive example when it is going to solid to gas, or when it is in equilibrium with solid to solid to liquid and liquid to gas. In this case, whatever the amount of heat that is required is delta H of fusion. This is called as delta H of fusion. Here, this is called delta H of vaporization. Okay. Now, for first case, if you notice that whether it is a fusion or whether it is an vaporization, it is always greater than 0. And second, delta S of the fusion is also greater than 0. Delta S of vaporization is also greater than 0. Okay. Now it depends upon whether you are operating at 0 degrees or any other temperature. So I can say that at 0 degrees Celsius, okay, considering the P atm is, atmospheric pressure is 1 atm here, okay, external pressure is 1 atm here. In that case, delta G of the fusion will be equal to 0. And the temperature can be calculated as delta H of fusion by delta S of fusion. And this is what we call it as melting point of the solid, a melting point of the water here. Got it? Melting point of ice. Okay. But if you are operating, let's say at 10 degrees Celsius, okay, if you are operating at 10 degrees Celsius, now what I can say, at 10 degrees Celsius, solid will have more free energy to move on to liquids as compared to liquids to move on to solids. So reaction will be more in the forward direction, which means delta G will be less than 0 in such cases. Delta H of fusion will still, I mean, now you do not use the word fusion, I'll simply call it as delta H of reaction. That will be greater than 0, or delta S of the reaction, or simply delta S of the equation in this case will also be greater than 0. But what if you're operating at minus 10 degrees Celsius? In that case, delta G value will be greater than 0 because now it will be mostly in the backward direction. Delta H of the change or phase change will be less than 0. Delta S of the phase change will also be less than 0. Correct? This is what you need to understand at different temperature cases. Likewise, if it comes to liquid to gas, you know that at 100 degrees Celsius, when the atmospheric pressure is 1 atm here, in that case, delta G of the vaporization is also 0 and T will be equal to delta H of vaporization by delta S of vaporization, which we call it as boiling point of water in this case. And likewise, if you have 110 degrees Celsius, okay, delta G value will be less than 0 because it will be more in the forward direction. Delta H of the reaction will be greater than 0. Delta S of the reaction will be greater than 0. But at 90 degrees Celsius, now the reaction will be more in the backward direction and delta H of reaction will be less than 0 and delta S of the solution will be less than 0. Now notice we can always apply something called pressure temperature equilibrium. Correct? How is that going to look like? Suppose if it comes to pressure, vapor pressure versus temperature, in the case of water, you will notice the graph would go like this. The equilibrium graph will be like this, wherein this part is solid, this is liquid, this is gases. And 1 atm line will be somewhere here. This is that 1 atm line. Okay, this is 1 atm line. So at 1 atm, where the liquid gas equilibrium is touching, that is called as the normal boiling point of water. And if it is touching solid liquid equilibrium, that is called as the normal melting point. Remember NMP and NBP. Okay. If it is standard melting point or standard boiling point, that means it should have been at 1 bar. 1 bar is the standard value, 180 is the normal value. Okay. So now for water, in the case of H2O, we know that this happens at 0 degrees Celsius, that happens at 100 degrees Celsius. Now notice it carefully. This is serving an equilibrium. This line, suppose if you notice this particular curve, this is serving the equilibrium of H2O solid to H2O liquid. While this equilibrium is serving as H2O liquid in equilibrium with H2O gas. Okay. In such case, let's say this is the first equilibrium, this is the second equilibrium. In first equilibrium, you notice that as pressure increases, okay, suppose if I increase the vapor, if I increase the atmospheric pressure or external pressure, then you are going into this direction, right? This is external pressure increase. So in which particular zone you are ending up? You are ending up into liquid zone. Liquid zone means forward direction. So reaction will move in the forward direction, correct? As pressure increases. So if you are operating at a higher pressure, reaction will go in the forward direction. So remember, at 2 atm or 1.5 atm, if you are operating this equilibrium, the reaction will start moving more in the forward direction. It comes with the fact that liquid has more density than solid. So it will occupy relatively lesser volume. That's why it is moving in the forward direction. Same way, in case of second equilibrium, you will notice that as pressure increases, reaction is going in the backward direction, because again here also as the increased pressure is observed, the reaction is actually moving towards the liquid direction. Correct? This is the exclusivity which you will notice only for water. Correct? Now, similar thing if you do it for carbon dioxide, for example. Okay, carbon dioxide or general cases are all the same. So if you compare pressure versus temperature, this is for carbon dioxide vapor liquid equilibrium. In that case, it would go like this. Okay, where this is solid, this is liquid, this is gas. In fact, the gaseous part is very, very less. That's why carbon dioxide is hardly found in the liquid state. And now you notice that this line will be that one ATM line here. Okay, so this will be the normal boiling point. This will be the normal melting point, correct? And now notice, as pressure increases, okay, this is first equilibrium, this is second equilibrium. So if you compare the first equilibrium, as pressure increases, reaction is actually going in the solid direction. So reaction will move in the backward direction. And in second equilibrium also, right, as pressure increases, reaction will now move back again into the backward direction because you are going towards the liquid region only. So water is an abnormal case, everybody. Water is an abnormal case. Otherwise, rest of all the compounds will actually have a behavior similar to that of carbon dioxide. Clear, everyone? So this is the physical equilibrium cases that you need to understand. Okay. Now, last thing is how exactly the uh, equilibrium changes as you start changing certain components here. So let me put it as an example here. Suppose, so let's say I have N2 plus 3H2. Both of them are gas here, and it is in equilibrium with 2NH3 gas. Now imagine, suppose it was originally at equilibrium. This was originally at equilibrium, and N2 is like this. N2 is changing like this. Okay. Let's say H2 is also decreasing. Concentration of H2 is decreasing like this. And ammonia is increasing like this. And this is where it was at equilibrium. This is the equilibrium, right? So this is the first equilibrium, correct? Now what we did, we added some amount of nitrogen. So if you add some amount of nitrogen, right, at first equilibrium, if I add some amount of nitrogen, as per Le Chatelier's principle, it should move in the forward direction. And since the reaction will move in the forward direction, correct? Now the concentration of N2 will decrease again, H2 will decrease again, and ammonia will increase, correct? So this is NH3. So how do we address that? You will start writing like this. You show that nitrogen concentration is increased. From here, it is decreasing again. Hydrogen was not added, so directly you show decrease here. Ammonia was not added, again you will show like this. So that means here we reach to the new equilibrium. This is the second equilibrium, correct? So in the first case, what did we do, everybody? We added N2 gas, okay? Second, what if we add ammonia here? Add NH3. If I add NH3, reaction should go backward direction. So which means ammonia composition should decrease, hydrogen should increase, N2 should increase. But because you added ammonia first, so you need to show it like this. And from there, you need to show that there is a decrement. And from hydrogen here, it is an increment. And for nitrogen, again from here, it is an increment. Got it? So again, it will reach to a new equilibrium. This is the third equilibrium that you have achieved. At this stage, what I did, I increased the temperature. Assume this reaction is exothermic. Okay, this is exothermic. If it is exothermic, what should happen? As you increase the temperature, reaction should go in the backward direction. So if it has to be backward direction, then nitrogen value will again increase, hydrogen value will increase, and ammonia value will decrease. So again, I'll reach to a new equilibrium, right, where this will be the fourth new equilibrium after increasing temperature. Now imagine here I add an inert gas at constant pressure. Now what if I change the what if I keep the pressure constant? Which means volume will increase on adding inert gas. If I increase the volume, reaction will go in the direction where the number of moles are increasing. Which direction moles are increasing? On the backward direction. So again from here, you will notice the graph, I mean, it will start moving in this direction. From here, it will go up. up and here like this. Got it? Clear? So you notice that when inert gas is added and temperature change happening, there is no rise of some moles or something like that here. Got it? So directly you will notice it this way. Okay? Acha, sorry. All of them, my mistake. Sorry. From here, as soon as you add the inert gas, my mistake. See, as soon as you add the inert gas, what happened? Volume got increased. As volume got increased, what should happen to the number of moles of nitrogen, sorry, concentration of nitrogen, hydrogen, and ammonia? All of them should decrease. So you should start from here, decrease, decrease, and decrease. So from here, you have to achieve the equilibrium. So ammonia would decrease now because it is going in the backward direction. Hydrogen will increase now, nitrogen will increase now. Got it? This is the way it will operate. Here, just a minute. Right. So this is the way it will go. So now it will achieve a new equilibrium from here. This will be the fifth equilibrium achieved after this. Clear? Everybody? These kind of questions are asked. You would be given this kind of graphs. You need to predict what is happening in which case. Okay. So theory wise, if you ask me, chemical equilibrium has only this much amount of theory. Correct? One part which I haven't discussed, I thought maybe I'll discuss with the questions. I'll just write down that here. Correct? That is relation of alpha vapor density at equilibrium and vapor density initial. These are the values. Okay. So suppose if you have an A gas, it is dissociating into n moles of B gas. I can write this as 1 minus alpha and n alpha. So at equilibrium, total number of moles will be 1 plus n alpha minus alpha. And you know that number of moles will always be inversely proportional to the density. So therefore, initially we had only one mole. So we can say number of moles initially is directly proportional to, inversely proportional to initial density, and at equilibrium, it will be proportional to equilibrium density. Usually, conventionally, we always take this as capital D, we take this as small d. So in that case, we can write n equilibrium by n I will be equal to d by d. So that is equal to, at equilibrium, it is 1 plus n alpha minus alpha by 1, which is equal to d by d. So from here, I can write alpha is equal to d minus d by n minus 1 into d. Now, basically, these d values can be interchanged with vapor densities. Vapor density initial minus vapor density at equilibrium divided by n minus 1 into vapor density at equilibrium. Vapor densities can also be replaced in terms of molecular weight. Molecular weight initial minus molecular weight equilibrium divided by n minus 1 into molecular weight initial. This way. This is the way you can relate with vapor densities and alphas. I hope all of you understood this logic. Right. Okay. Right. So first one or two questions I'll explain. Then afterwards you can start solving. Okay. So let's see this question. Vapor density of N2O4 at a certain temperature is given. What is the percentage dissociation of N2O4 at this temperature? Okay. So basically vapor density initial, correct, will be equal to molecular weight by 2. So which is 92 by 2, which is 46. And vapor density at equilibrium is given as 30. Therefore, if you have to write alpha value, which is equal to vapor density initial minus vapor density final or equilibrium by n minus 1. What is n now? You always need to check out how many moles of product you are getting for every 1 mole here. So for 1 mole, you are getting 2 moles. So N value is 2. So 2 minus 1 into 30. Got it? So that makes it 16 by 30 here. Clear now? So how much is the percentage dissociation? Which is coming approximately close to 53 point, I mean 0.53, 0.53 percentage, which is, sorry, 0.53, or percentage alpha is 53.3 percentage. Okay. Easy. Right. See. Next one. Okay. I want you to do the third one. Please try this out. I'll give you a minute's time, then I'll discuss. Those who are still trying, you can go check this, complete that working. Others, you can just look into it. At a pressure of 5 atm, uh, ammonia at a pressure of 5 atm and H2S at a pressure of 10 atm are introduced into the evacuated vessel here. Okay. And total pressure of the gases after a long time. After a long time means after it achieved equilibrium, beta. When it reaches equilibrium. So I can say NH3 plus H2S is becoming NH4HS. Correct? And Kp value for this will be equal to 1 by 62.5. And here this is 5 and this is 10. This wasn't there. So you will have this as 5 minus X amount, 10 minus X amount of pressure lost. And we don't have to worry about this one. This will be Kp. So I can say that Kp value will be equal to 1 by 5 minus X into 10 minus X for this equilibrium. That has to be 1 by 62.5. Got it? So 62.5 is equal to 5 minus X into 10 minus X. Right? So how much we are getting? 50 minus 10 minus 5x, 5 minus 5x here plus x square. So we are getting this as x square minus 15x plus 50 equal to 62.5. Got it? So how much is the x value here? X square minus 15x, right? Plus, yeah, yeah. So minus 12.5, that is equal to 0. Okay. So how much is the x we are getting, beta? You try that. 15 plus minus under root of how much is this value? 225 plus 4 into 1.12.5, that divided by 2. Let me just check it out how much I'm getting. Plus something I made a mistake here. 50 oh, sorry. Yeah, I made a mistake here only. Oh, okay. See, check out. We have 5 and 10, right, beta? Oh, Kp, suppose if you notice Qp, what is the value of Qp, beta? Qp value itself is, 1 by 50. Compare that to 1 by 62.5 here. So you can see 62.5 is actually greater than 50, which means even at the reverse equilibrium, if you put it out, so this amount of values, that 5 and 10, are not sufficient amount to form this NH4HS. Got it? So which means if you have this as N2 plus, I'll put the reverse way here. So I'll have this as NH4HS solid if it is with NH3 gas plus H2S gas here. So if this is 10 and this is 5, now you tell me what is the QP value here for this one? QP value is 50, which is less than Kp value. Acha, if it is less than Kp value, the reaction should go in the forward direction. But do you think you have a resource of ammonium hydrogen sulfide? No. So if since there is nothing of ammonium hydrogen sulfide, do you think they will progress in the backward direction? Not at all. So which means what will be the amount? It will always remain 15 atm. So no reaction will take place here. So it will remain 15 atm. Clear? Everybody understood?
So can you explain the last bit again?
Yeah, what I said. See, you learned that when it comes to reaction quotient, if it is less than Kp, the reaction will be drive in the forward direction. Barabar? But to make the reaction drive in the forward direction, you need to have the reactant, na beta? But we didn't take any reactant at all. We took only two products. So how will the reaction go in the forward direction? No. So even if these two tries to go in the backward direction, that is completely non-spontaneous change. Okay, a highly unfavorable change. Got it?
Okay, got it.
Right. Please try question number 9. Let me add that here. Others, just check it out. Ammonia gas plus H2S gas. Okay. So we know that this is present at 0.5, and as this decomposes, it will become plus X, and this will be 0.84, right? Sorry, this will be X. So 0.5 plus X into X, that should be equal to the uh, Kp value, or rather I would say the total pressure is already given to us. We can just use that value. So which is 0.5 plus x, that should be equal to 0.84. So 2x is equal to 2x is equal to 0.34. So x is equal to 0.17. So we got the x value here. So pressure of ammonia will be equal to 0.67. Pressure of H2S will be equal to 0.17. Okay, this is what you guys multiplied. Let me just check if the answer is matching. 0.67 to 0.17. Yeah, so Kp value is coming out to 0.1139. Got it? So I'm sure this wasn't that difficult. Yeah, good. Most all of you got that right. Yeah, try 14th one. I think you can do it. Sorry, leave that. I'm sure you guys can do that. Yeah, try 25th one. Please try this now, everybody. See, A and C is not a difficult case because you must have noticed that A was initially taken as 1 molar. So obviously, as the equilibrium reaches A, B, C together will remain as 1 molar. So there is no problem in A. A is correct. And you also see that the overall reaction is basically A forming A only. So which means K1 into K2 into K3 should be equal to 1. So which makes it K1 is equal to 1 by 0.4 into 0.6. That makes it as 1 by 0.24. Got it? So this C is also not a problem here. Now, where you are missing out is this one. Now notice A is giving B. What is the value of K1? K1 is 1.0.24. It is approximately 1 by 0.25. I can write it down, which means approximately 4. Now, if Kp value is 4, so would it remain it as more as A or more as B? It will remain more as B, na beta? Now, see, B will be converting into C. What is the value of K2? K2 value is zero point 0.4. So that means it will be remaining more as B or C. It will remain more as B. This equilibrium is also pushing reaction more towards B. This equilibrium is also pushing equilibrium more towards B. So tell me which is thermodynamically more stable, A, B or C? B. B is more stable. Okay. So B is most stable in terms of thermodynamics. Okay. So that also gives the idea that A is least stable because this equilibrium value is very high. We suggest that A forming B is least likely to happen as compared to C forming B. So therefore, this D is also correct. Clear with this point? Harjita, did you understand that?
Oh, yes, sir.
Samyak?
Sir, can you explain last option again?
Right. See, what I said, A forming B is a higher value, beta. A value is higher means reaction will start moving in the forward direction, correct?
Yes,
The
sir.
reaction will always try to move in the direction where it is more thermally stable. Got it? So you can see B is observed to be more stable as per the first equation. And is B becoming unstable? Actually, no. In the second equilibrium is explaining. Because K2 is less than 1, which means this reaction will be more likely to be in the backward direction than forward direction.
Okay, sir.
Correct? So the most stable one is B, okay, and the least stable one is A.
Okay, sir, got it.
Yeah, right. One second. Let me push one more question to you guys. What we know that is that the vapor pressure of bromine liquid, Br2 liquid, is 0. Sorry, vapor pressure of Br2 liquid is 0.25 atm. Okay, and the total pressure is 2.25. So which means the vapor pressure contributed by Br2 liquid is 0.25 here, and which leaves the pressure of the dry gases, pressure of the total pressure of dry gas will be equal to 2 atm. So I'm sure you must have got that part. And moreover, to maintain the 0.25 atm of pressure, how much amount of bromine must be in the liquid state here, in the vapor state here? Let us put that in terms of number of moles. So we can write it as PV by RT. So that is equal to 0.25 into volume. How much it is given? Yeah, 164 divided by 0.0821 multiplied by temperature, which is 300 kelvins. Got it? Now solve it. I think this is coming as 5 by 3 moles. I'll keep this aside. Okay. Let us keep this as 1. Now coming to the actual equilibrium which is happening, which is Br2 liquid plus Cl2 gas, that is in equilibrium with 2 BrCl gas. Okay. And Kp value is given as 180, right? Initially this is given as 10, right? And we do not have to worry about how much was bromine. Okay, so this is given as 10, and now we need to check out how many moles have been lost here. So check out of this 10 moles, less x moles have been gone, so 2x moles have been formed. So total number of moles are 10 plus x. So that makes it 10 minus x by 10 plus x, which is the mole fraction, into total pressure. Achha, how much is the total dry gas pressure? 2 atm. So into 2, so 2x by 10 plus x into 2. So these are the partial pressures. So I can write that partial pressure of BrCl square by partial pressure of Cl2 must be equal to Kp. So that is equal to, so you can see this as 4x by 10 plus x, whole square, or rather I'll write the 2 like that only. So 2 into 2, 2 square, this whole square, this divided by 10 minus x by 10 plus x into 2, correct? So that should be equal to 1. So the 2 will get cancelled. 4 2s are 8 will come. So 8x square by, this will become 10 minus 100 minus x square, correct? So 100 minus x square, that should be equal to 1, correct? So solving this, how much we will get? X value, you are getting this as 10 by 3. I'm sure all of you must have got this. This is what you are thinking, that this is the minimum moles which you need to have. But listen up. Suppose if you compare this, right? How many moles of amount we need to have to maintain this Br2 liquid? Because minimum, how much we need to have? We need to maintain this much amount. This X amount need to be lost, and at the same time, vapor pressure also maintained. Vapor pressure also need to be maintained by 5 by 3 amount. Okay. So what is the X value here? 10 by 3. Correct. So X value is 10 by 3. So number of moles of Br2 liquid required to maintain all of this will be minimum 10 by 3 required for this one. Correct. Here. And another 5 by 3 is minimum required to keep it in vapor state, because otherwise we cannot get that bromine, right? So total that makes it 15 by 3. So total how many? 5 moles. So you forgot that 5 by 3 part of it. Clear everybody?